guys, this is a video lecture for section 16.5 on curl and divergence of vector fields. Heads up as a little bit of a motivation for this section before I get into it with the gradient here. Wanted to discuss why we're shifting gears a little bit from line integrals today, because we're not working on line integrals today. As the past couple sections, I've taught you different ways that we could approach these. You could do line integrals directly, fix your bound, your function, your differential. We could do them with the fundamental theorem of line integrals. That worked for both 2D and 3D vector fields. And then most recently in class on Friday, we introduced Green's theorem, which was a technique for working specifically with 2D vector fields over closed curves. Now you notice there wasn't a 3D analog. It turns out that we need a little bit more firepower before we can work with those 3D vector field line integrals. So we're starting on that path today. And I have to introduce a couple new operations on vector fields for us to do this. Now, to go ahead and get started with introducing those operations, I'll have you guys recall our notation for finding the gradient of a scalar function. Right? If I've got a scalar function, we need to find the gradient of f as this vector where you just took all of the partials and shoved them into a vector. Now, there are a couple other ways that we could denote the gradient. Sometimes you saw GRAD instead of the little upside down triangle, this del operator here. Now, some comments on, if I could get my pen going straight, some comments on this del guy as a operator. This is what we're going to be manipulating today to define our operations of curl and divergence. What I'm going to go ahead and do is this. We will let this del operator, let me draw a better upside down triangle in that. We'll let this guy actually be a vector operator. This will look like the partial with respect to x, the partial with respect to y, and the partial with respect to z, all shoved into a single vector. This is a little bit strange vector for us, but after seeing dr as a differential, dx, dy, dz the other day, hopefully this doesn't look too weird. Now, I'm not saying that in this definition that these guys explicitly are functions, right? ddx in and of itself, ddy and ddz, these are all operators themselves that tell you to do something, right? Take a partial with respect to x or y or z in this last component here. So how I want to interpret this is just a vector full of operators, but I can manipulate this vector just like I would any other vector, right? So once I make this guy a vector, I can treat it like one. Okay, I can treat this like a vector. As an example, I can do things like scalar multiplication, right? If I do scalar multiplication and say something like del f, or gradient of f, well, what I'm doing here is my del operator that I just wrote above, okay, line up or so, but this is being multiplied by f. Well, if I go to simplify this, what this is saying is I'm taking a partial with respect to x of f, I'm taking a partial with respect to y of f, and I'm taking a partial with respect to z of f. Or we maybe more commonly see this written as fx, fy, fz. It all means the same thing, right? So you notice, weird list of symbols, we put them in a vector, we're going to treat it like a vector, right? So we're going to allow vector operations on this. Now, scalar multiplication isn't the only thing that we could do with my vectors. Recall cross products were a thing that we could do with vectors. Just in case you forgot the formula, this is a recap on how we find it. If I'm crossing two vectors, x, y, z, and a, b, c, okay, these guys here, I gave you guys this diagonals trick for trying to remember the formula. If I copied the components of my first vector over my second vector, repeating my first term, what I could do is basically look at maybe Xing out a column if I was interested in that particular component. Like say for example, I am interested in my first component, so I ignore that guy. And then I look at the diagonals in the box immediately next to that column. Okay, if I take products along those diagonals and then take a difference, that's what happened in my first component, right? So here I'll get cy minus bz. Now if I wanted to repeat that process for my second component, I end up looking at these guys and the diagonals that are corresponding. I get az minus cx in my cross product. Okay, so on and so forth. Now really what this pattern is trying to represent is, if you aren't in linear algebra or haven't taken linear algebra, this will be unfamiliar, but if you're in linear, this is the determinant of the matrix I, j, and k, along with x, y, and z and a, b, c all put into a matrix together. Now, we were talking a moment ago about performing vector operations on that del operator put in a vector. Well, this is how you get, if I could scroll back up to the top here, this is how you get something that's called curl of a vector field, right? To go through this definition, I'm starting out with a three-dimensional vector field. Okay, we're only doing this on R3, not on R2. And I'm assuming that the partials of each of those exist. Then I can take my curl by performing a cross product of the del operator with f. Okay, so that means if I, take my del operator in f, you could set it up in that determinant of the matrix like I discussed on the last slide, or do your little diagonal trick to remember your formula for how to get all the pieces together. At any rate, this conglomeration of partial derivatives in a vector here, this is what I want to think of as my curl of f. Okay? Now, a question, this thing looks like a hot mess. What is it supposed to actually tell us? Well, let me go ahead and scroll down here. Curl tells us the tendency of a vector field to rotate about a point. Now, we'll recall that vectors are quantities that have both direction and magnitude. So if you take curl, okay, I'll scroll up a moment here. Curl is a vector, right? You crossed two vectors, you got a vector back. Okay, the vector that you're getting is going to have a difference of partials in component 1, a difference of partials in component 2, and a difference of partials in component 3. Okay, that's three different things. I get a direction associated with that. Now, the direction, what this is going to tell you, if you plug the point of interest, or a point of interest, into that vector field function above, it's going to spit out a vector. And what that's going to tell you is the axis of rotation locally near that point. Okay? Somehow, if you plot your vector field, remember the graphs of vector fields look like, graphs of a bunch of arrows everywhere. Near that point, this is saying that it looks like it's spinning specifically about that axis of rotation. Now, the magnitude of your vector, your curl vector, once you plug a point into that curl formula, if you took the magnitude of it, what this is going to tell you is the strength of that rotation, right? Large magnitudes are going to be rotating rather forcefully. Small magnitudes mean that it's barely rotating, but it does kind of look like it's rotating. Okay, so I'll give you guys some concrete examples that we can physically look at here. Let's say that I want to compute my curl for this given vector. Now, just for sake of graphing this thing, if you look at cross-sections of the vector field, they'll resemble what I've drawn right here, just so we have a little bit of a context for this example. if I want to compute my curl for f, well, we can go ahead and use that formula. We want del crossed with f. Or this is going to be that d dx d dy d dz vector crossed with negative y, x, and 0. You can do this with the determinant if you actually understand what a determinant is from your other classes. If you have no clue what a determinant is, we can go ahead and use our cheap diagonal trick for computing this here. My cross product vector that I'm getting here should be, if I ignore my first component and look at my associated diagonals, this is going to give me my partial with respect to y of 0, that's 0, minus my partial with respect to z of x, well that's also 0. Okay, let's say that I pick a different ink color here. If I'm interested in my second component, that means that I want to look at these diagonals. Well, that's going to give me my partial with respect to z of y, that's 0, minus my partial with respect to x of 0, this is also 0. Now this isn't a totally boring example, I promise. We'll go back in with the last color here. If I'm interested in my third component, well, there's not a full box over here, but there's a full box over to the left. I'm looking at my partial with respect to x of x, hey, we finally get something, minus my partial with respect to y of negative y. Well, that's going to be negative 1. So all in all, when I go to compute this guy here, this Christmassy looking thing here, my end vector ends up being 0, 0, 2. So what this is going to do, if I just said that, oops, that's a little tilty there, if I draw my vector field, the cross sections of this thing will kind of look like, you know, you can see in the graph that I drew above, like they're spinning, okay, about my z-axis. We have just said that this guy, 0, 0, 2, this is my curl vector, right? That guy is my curl of f. Now, if you want to be a little bit more precise about how this vector tells me how I'm spinning, this does behave according to the right-hand rule. The way that you want to think about this is point your thumb in the direction of the vector, okay, so your thumb points up. If you try to curl your fingers closed, that's going to specify the direction of the rotation. Now, that makes sense because if you point your thumb upward and swirl your fingers closed, you know, they will point in roughly the same direction. That these vectors seem to be swirling around my z-axis. Okay, let's try this for another example. This one will be really, really easy. Let's compute the curl for my vector field f, which is the constant vector field of 5, 1, 3. Okay, so again, your curl is given by the del operator crossed with f. So again, d dx, d dy, and d dz crossed with a vector 5, 1, 3. Now, if we're smart about this, let's think kind of critically here. Every single one of those things that popped up in the formula had us taking partials of constant functions, right? So even if I get my ordering totally mixed up, right, you know, my shortcut had me writing out each of these partials and each of the terms in my function that I had to work with. If I'm looking at something like, you know, for my first component, this box here, you got a y partial of 3 and a z partial of 1. it doesn't matter what letter you were taking a partial with respect to, all these are constant functions, right? So we're getting 0 minus 0 here. You're going to get a similar term over here, and you're going to get a similar term in your third component. Your curl vector is just going to be 0, 0, 0. Okay, so curl of f, this is just the 0 vector. Now, I told you guys that curl is supposed to measure your tendency of a vector field to rotate or spin about a point. Well, hopefully this should make sense if we think about it, right? What does my vector field look like? Well, if I go out 5 units, 1 unit, and then 3 units, okay, we could go ahead and roughly sketch my reference box here just to tell me where this point is. So here is my vector from the origin, 2, 5, 1, 3. Now, a comment, since this is a constant vector field, that vector is going to appear basically everywhere in this vector field, right? That's what constant functions do. It doesn't matter what point you plug in, they're still going to spit out the same exact thing. So I've got the same vector pointing everywhere in this vector field, and I just computed the curl of it. Right? If curl is supposed to tell me the tendency of a vector field to rotate, there is no rotation going on here, right? Everything is pointing in the same direction. So of course, no rotation. If you wanted to compute the magnitude of the rotation, well, there's none. So we're stuck with the 0 vector. If not obvious what this is going to tell me, you know, is 0 curl, okay, 0 vector, for curl, this basically means no rotating. Okay. I'll move on just to hit a couple theorems about this quantity that we've learned how to compute here. One, if you've got a continuous scalar function with continuous second partials, your curl of that gradient, okay, we can't take curl of scalar functions, we take curl of vector fields, but the gradient function is a vector field. If you go to take curl of a gradient, you get the 0 vector back. Okay, so kind of the idea of what we're doing here, you can note sort of the algebraic idea for this. If you go to just grind out the computation, you know, compute the gradient, take all your partials there, compute your curl, so you're taking another set of partials there. Notice that in doing this, you're doing 2 rounds of partial derivatives. This basically happens by my equivalence of my second mixed partials. So what's happening in every single one of those component parts of your curl function, and we can go ahead and just think about this, I won't worry about writing it out verbatim. When you go to take partials, one of the components, you've basically got a xy and a yx partial that you're subtracting, they'll cancel each other out. Another one, you'll have a yz and a zy partial, they'll cancel each other out. That'll happen in every single one of these components. So at least that's kind of the algebraic way to think about it. If you want a, you know, geometric way to think about it, it's this. Recall that your gradient tells you your direction of steepest increase, and my curl tells me tendency to rotate. If I'm trying to constantly point in my direction of steepest increase, well, I'm probably not going to be going in a circle unless I'm in an Escher painting of some sort. You know, your direction of steepest increase isn't going to send you running around in a circle. So you shouldn't get rotation in a vector field like this, right? So we've got the algebraic idea Or we've got the geometric idea, your direction of steepest increase doesn't loop around, right? You're not going to be sending yourself in circles here. So no rotation in that vector field. The second theorem that I wanted to bring up relevant to curl. If we've started with a vector field that's defined in all of R3, we've got continuous partials and a curl of 0. What that's going to tell me is that my vector field is conservative. So really the idea here is just apply your above theorem, right? We're really kind of running that into the ground here. If I'm going to work with some sort of conservative vector field, that means that I'm working with something that probably looked like a gradient in the first place. That's all that being conservative means, is that f is a gradient. If I'm then taking the curl of something that looks like a gradient, by that above theorem I should get 0, right? So kind of the idea is that we're still getting, or at least shooting for, my equivalence of my mixed partials. Another way to think about this, this is kind of a similar notion to checking if my PQ, okay, I'll scroll down and give myself a little bit more room here. Similar notion to checking if that guy is conservative, okay, by verifying if dp dy is equal to dq dx. Right, we've done that in previous sections. Check if the two-dimensional vector field is conservative to see if it's worth trying to find a potential function for it. We said that if my p looked like an fx and if my q looked like an fy, okay, does that happen? If that's the case, this guy looks like fxy, this looks like fyx. If both of those are the same thing, we're conservative. You're basically checking the mixed partials again. Just there's a big formula to verify it this time, right? So let's go ahead and try this with an example. I've got a vector field spelled out here that I want to see if it's conservative or not. Now, if we look at this with a critical eye, probably the vector field came from a gradient of the function e to the x y sine z. You'll notice that if I take a partial of that with respect to x, it spits back out my first component here, my x component. If I take a partial with respect to y, the y drops off. If I take a partial with respect to z, I get a cosine term. Okay, so my scalar function, my potential function that I take a gradient of to get this, is basically just the function in the first component. So definitely this is conservative, but we can also verify it with the curl, because, knowing that this really looks like some sort of fx, fy, fz here, let's see if we can actually set this up, right? My curl of f, this is always my del operator crossed with f. Make sure that you get your order straight here. So if I wanted to do my scratch work, this is the d, oops, pen's kind of flaking out here, my d dx, d dy, d dz, oops, I'll go ahead and just throw that guy down one more line, erase some of the stuff that I don't need here. And then for my scratch work, I will write my relevant functions, my e, x, y, sine z, down here, just to give myself a little bit more space, my e to the x sine z, and my e to the x, y cosine z, down here, my e to the x, y sine z. Okay? So, if that guy is my scratch work, let's see if we can actually crank this out. For my first component, okay, I'm worried about dx. That means that I need to worry about a y partial of this guy and a z partial of this guy. Now again, notice what we're doing here. We're taking a y partial of basically what should be fz, and we're taking a z partial of what should be fy. We're expecting to get 0 based off of the equivalence of mixed partials. So let's verify this. If I take my necessary y partial, I get e to the x cosine of z. If I take my necessary z partial, I am subtracting off e to the x cosine of z. So sure, that comes out to 0. For my y component, I'll trip to another color here, I am now looking for my z partial of this function minus my x partial of this function. This should be a z over here if I had copied this correctly. If I go to take my z partial, well, that sine z is going to turn into a cosine z. If I take my x partial that I need to subtract off, well, the exponential function doesn't do anything. So again, I'm getting things that cancel out. And then in my last component, again, I'll switch to another color here. What I'm looking for is my x partial, okay, of this guy, minus my y partial of this guy. If I wanted to fill that in, you know, this is basically going to be an e to the x sine z minus another e to the x sine z. Okay, this obviously, if I go to simplify everything, does cancel out to the 0 vector. Okay, so what I'm getting is that my curl f is 0, so my f is conservative. Okay. Now I mentioned earlier this was the curl and divergence section. I haven't quite gotten to divergence yet, so without further ado, I'll go ahead and define that guy. This is also based off of manipulation with the del operator, but instead of the cross product, we're doing the dot product this time. If we've got a three-dimensional vector field and we want to compute divergence, the manner in which we do this is you take a dot product. That ddx, ddy, ddz del operator, we'll just dot it with our function. So that way, you're taking an x partial of your x component, a y partial of your y component, and a z partial of your z component, and then just sum everything together. Big reminder here, your dot product is a scalar function, okay? You shouldn't get a vector back for this. I know I'm still seeing a couple people making that mistake occasionally on homework assignments, and even on the last test. Okay, you should get a scalar back. No vectors once you dot. Now, what does this guy tell us? This tells us the tendency of vectors to diverge away from or towards a point, hence divergence. If positive, you know, your vectors point outward. On the other hand, if you're negative, then your vectors point inward. Okay, what do I mean? Maybe some sort of situation like this up top versus a situation like this guy on the bottom, right? Am I pointing outward? Am I pointing inward? On the other hand, you know, hopefully we can gather this similarly to the last operation, curl. If you get something that's neither, if you get 0, your vectors aren't really pointing outward or inward towards your point. As a comment, in that last situation, if your divergence is 0, you call the vector field incompressible. Now, what this is a nod to, one of the situations that maybe you might be worried about curl or divergence for is if you're a person that studies fluid flows. Maybe things like airflow around an airfoil, or if you're studying ocean currents, or things like that. If you actually think about these vectors that we're drawing here as representing maybe velocity of particles in a fluid flow, you don't really want your particles to be doing these things, right? You can't really compactify that fluid down to a point or really have it expand outward significantly. Or at least, for things like water, you would probably not expect lots of stuff to be heading into a single central point. It has to go somewhere, right? So this is a nod to those sorts of vector fields. If you get a divergence of 0, you get an incompressible fluid flow. As an example, consider that 513 example that we had before, the vector field in which we had the constant vectors all pointing in the same direction. If you wanted to compute this, we've got del dotted with 513. If I perform that operation, this is d dx d dy d dz dotted with 513. Well, this is an x partial of 5, which is 0, plus a y partial of 1, which is 0, plus a z partial of 3, which is 0. We get 0 divergence. So, if all the vectors are headed in the same direction, they're not really headed outward. At any point, you have about as many, a good way to think about it is you have as much heading into a point as you have heading out. Okay, there's not really a net gain outward, a net outward, or a net gain inward. To contrast this, though, if I consider something like the vector field xyz, now to think about this at any point, let's say I'm at like 1, 1, 1, we'll pretend that's here. Well, if from here to here is the 0, 0, 0 to 1, 1, 1, that same exact 1, 1, 1 is the vector that I want to draw at 1, 1, 1. And we're going to get a similar model for every other point. At a particular point, you think about the distance from that to the origin, and that's the exact same vector that you want to draw outward there, right? So here, I would want to draw this guy, etc. You'll notice that in general, all of these are just heading away from the origin. So we should expect a positive divergence here. You can confirm this by actually computing, right? So if I want the del operator dotted with x, y, z, this is me taking my d dx, d dy, d dz vector and dotting it with x, y, and z. That means that I want an x partial of x plus a y partial of y plus a z partial of z, and I'm getting 1 plus 1 plus 1 is 3 here, so I get a positive divergence. Now comment, just for sake of making these examples fast, I did, give you guys a lot of stuff that spits out constant values. Okay, constant values for divergence, constant values for curl. These don't necessarily happen. I could have gotten a function of x, y, z here. And if you're interested at the curl or divergence at a particular point, you plug that in to the function that you get at the end. Okay, so you could have different vectors to rotate around, or different tendencies to go outward or inward for your vector field based off of what function that you get on the end here. Just so happens here, we've just got a constant all the way across this vector field. My divergence ends up being 3. Now, I'll go ahead and close just on a theorem referencing your divergence and curl here, because these aren't totally disconnected ideas that we can't relate to each other. A theorem I'll close on is that if you have a vector field whose components have continuous second partials, if you go to take the divergence of the curl, you're going to get 0. Now again, there's a couple ways that we can think about why this works. Algebraically, stuff cancels, right? That's the big takeaway here. All of your mixed partials that you're going to be running into, you know, for each xy, there's going to be minus yx or something like that that'll offset it. All these are just going to knock each other out. So that's algebraically the way to think about this. The other way to think about this, if you wanted a geometric picture of what was happening, was the following. Think about a vector field that has non-zero divergence, right? Suppose we're heading all out, or maybe we're heading all in, who knows, but, you know, near some point, let's suppose that I'm heading outward. Well, if that's the vector field that I was dealing with, and this somehow came from a curl, well, keeping in mind that the way that curl works is it specifies an axis of rotation per the right-hand rule. So what's going to happen, if you think about the point that you are diverging from, is near the base here, we're getting disagreement from each of these vectors as far as where we are locally rotating. So this situation where if this was the vector field that you got for curl, this doesn't make any sense for us, right? You can't have a, you know, vector field full of vectors that are specifying your axis of rotation and have them be heading away from a point. That gives you disagreement in what sort of rotation is happening at the point. Okay, so here, you know, your rotation, my pen is kind of flaking out on me here. You know, my rotation field shouldn't diverge at a point. Okay? But at the very least, the nice test that you can pull out of this, if you know that your divergence of curl is always 0, well, if you took a divergence of some sort of a vector field and you didn't get 0, well, you know you couldn't have had a curl to begin with. So that's a direct application of this guy. If anybody has any questions on these, I should be checking my email in and out for the next week or so, so do please feel free to shoot me email questions if you have them on the homework. With that aside, the assignment regarding this and regarding Green's theorem should be coming up for you guys right when we come back from break. Again, let me know if you have questions, and I'll try to keep in touch with you guys over that. Have a good break, everybody.